In the last video, we looked at the case for the standing wave that was generated when the voltage reflection coefficient at the load is 1. So when we have a reflection coefficient of 1, what happens is this incident wave V bar plus, all of it will get reflected in V bar minus, and we saw how a standing wave is generated in that case. What we're going to do now is apply some mathematical analysis to understand the superposition of the two waves under more general conditions. In the video that I played, we saw that sometimes the two waves are adding constructively and maximum voltages are created at the antinodes, and a minimum voltage are created at the nodes, as we showed in the video. The ratio of the maximum to the minimum that's produced is called the voltage standing wave ratio, or the VSWR, sometimes pronounced VSWR. And the VSWR is the ratio of the voltage maximum to the voltage minimum for a standing wave on a transmission line. So if we were to mathematically express the maximum voltage, it's going to be whatever the peak value of the incident wave is, V peak, times 1 plus the absolute value of the reflection coefficient at the load. So we take the reflection coefficient at the load, which can range from 0 to 1, and the maximum value is going to be 1 plus that times the peak value. A similar expression can be developed for the minimum value along the transmission line. It's just whatever the peak value of the incident wave is, V peak, times 1 minus the absolute value of the reflection coefficient at the load. So we can use those two mathematical statements to create a mathematical statement for VSWR, and that is VSWR is equal to Vmax over Vmin, the ratio of the maximum to the minimum voltage at any point along the transmission line, and that's going to be Vp times 1 plus the magnitude of the reflection coefficient over Vp times 1 minus the magnitude of the reflection coefficient. And we can see straight away that the peak voltages will cancel out, so VSWR is just 1 plus mag of reflection coefficient at the load over 1 minus the mag of the reflection coefficient at the load. So we see that the VSWR is only a function of the voltage reflection coefficient at the load, and from this we can see that since reflection coefficient ranges from 0 to 1, plugging those numbers into this, we see that VSWR has to range from between 1 and infinity. S is another symbol that's often used for voltage standing wave ratio. So a S equal to 1 corresponds to a matched load, right? There would be no reflection coefficient, so it's 1 plus 0 over 1 minus 0. So there's 0 reflection, and a VSWR of infinity indicates that we had a short or an open at the load, which is the maximum possible mismatch, with the entire signal being reflected. When a lossless line is terminated in a matched load, what this tells us is that the peak voltage is the same everywhere along the line. As the degree of the mismatch increases, there's a greater variation in the range of peak voltages along the transmission line. I've posted a MATLAB script that I wrote to the Blackboard website that is going to help you visualize the effect of different reflection coefficients on the standing wave pattern. And I encourage you to play around with this file on your own after watching these videos. In the videos that I'm going to show here in a couple seconds, the green graph on these videos is going to be the incident wave, the blue graph is going to be the reflected wave, and the red graph is going to be the resulting standing wave. I'm going to start by replaying a video for the condition where the reflection coefficient at the load equals 1. So this is for either a open circuit or a short circuit. Technically, we should play a video for reflection coefficient as 1 or minus 1, but they end up looking pretty similar, so I'm just going to show you one. So again, the green line here is the incident wave, the blue line is the reflected wave. We can see the standing wave pattern where at the antinode we've got it going from a peak to a valley, and then at the nodes there is no change in amplitude. I want to stress this is the real voltage that you would measure with like a DMM or something on the transmission line. So not only is the voltage that you measure on the transmission line a function of where you measure it, now it's a function of also what time you perform that measurement at, right? So we've got a different RMS value here than we have here. Here our RMS value of voltage was 0. Here our RMS value is going to be, 2 div root 2 right there. In this video, we're going to plot the standing wave pattern that exists for the condition when the load is matched to the characteristic impedance of the transmission line, which means that there is no standing wave. So what you see here is the red wave is the incident wave, the blue wave is the reflected wave, there is no reflected wave, and the green wave is the addition of the red wave and the blue wave. Well, where's the green wave? Well, it's coincident with the red wave. The voltage in this case along any point of the transmission line is only determined by the forward traveling voltage wave. Since there is no reflected wave, no superposition occurs in that case. In this video, we're plotting a reflection coefficient of half. So we've got our incident wave here in the green. It reaches an impedance boundary that's got a reflection coefficient equal to 0.5. So this blue wave is the reflected, and we see the magnitude of the blue wave is exactly half that of the green wave. So via superposition of these two waves, this green wave and this red wave, we get this resultant, the green wave and the blue wave, we get the resultant red wave, which has a peak amplitude. You can see it goes up to 1.5, which is the sum of this and this at some points, and then decays down to a minimum here of 0.5. So some pretty bizarre behavior, because the red line, again, I want to stress, is the voltage that actually appears along the transmission line. So some pretty bizarre voltage behavior occurs because of the influence of this standing wave pattern.